me go to graduate school first. Right. See. So two things I need to let you know. First, how do you convert the PID control to output? This is really critical. I mean, if you have taken system control, external device, VGA, you have learned all this feedback stuff, but probably have never implemented any of the series into the real application. So the PID controller calculates the PID output, but that one cannot be directly used for the output of the motor. So how do we convert it into the output? Let's think about it. So what's the PID output? So what is the PID output over here? It's just a variable, right? It's a variable that merges the three types of errors. So it's a P plus I plus D, which gives you the PID output. And the PID output is being fed back to the input to find out the error, the updated error again, and then run through the PID and get output, and then feed it back to the input again, and so on and so forth, in order to get the smallest error. So the operation, the P and I and D, they are just the three components of it. That's the output is being fed back to it. So there are two things I want to emphasize. First, should this feedback a negative feedback or positive feedback? So the input is a set point, right? Just don't call it input, let's just call it set point. In our application, so what's the set point? So what is the set point of the car? 0 degree, balanced, okay? So that's the set point. But that's the ideal case. You're not going to get 0 degrees all the time. So it's going to be like plus minus 1 degree or 1.1, 1. Things like that. Okay. So would this feedback a negative feedback or positive feedback? Let's look at the diagram. So I'm not confusing you guys. So this diagram is way better than my drawing here. Is it a negative feedback or positive feedback? Negative, subtracting the PID output to compare it with a set point. So it's going to be a subtraction operation all the time. Okay, so that's a key point. It's going to be a negative feedback. And second, Second, how do you convert that PID output to the movement of the car? So the PID output is the angle, right? Whenever you get a bigger angle, you want to roll the wheel more or less. More. So we need to adjust the angle or correct the angle with more steps. So just want to repeat it. How many steps per 360 degree for the stepper motor we're using? How many? 200. You watched the video? I just guessed. You're not here. So a quick quiz question. So how many degrees per step? You're amazing. You were not here on Friday. But you definitely watched the video. Did you? Okay. 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 All right. Okay. So a bigger angle, we want to run different number of steps. A bigger angle, then more steps, right? So it's the reason I want to use stepper motor because they are accurate. Every step exactly 1.8 degrees. So now let's see. It's kind of tricky. How do we convert it in there? So the algorithm from the original author, he used time delays instead of directly convert it into number of steps. And we'll think about it why he has to do that. So we have to look at the code first so you know what I'm talking about, okay? Let me see if it's here. So the part one, does it have the PID controller? No, it doesn't. So the PID controller starts from part 2, the tutorial. So we covered the interrupt, okay? So if you have any question, you can ask, but interrupt should be clear. If you forget about that, then revisit the video to find out. And scroll down on the part 2 of the tutorial, so you can find out the critical part, the essential part of the code. So here it is. Okay. Why is 8192? That's the first question. Why one is larger than that number, then just directly assign this number to this accelerometer raw data. So what is that number? That's 1G. That's how many LSBs for 1G. Okay, and you can configure it. See, it's 8192 LSBs per G. And you have plus minus 4Gs, right? But in reality, because the sensor is not a perfect sensor, it's gonna give you like 82, 93, things like that. And whenever it's getting larger, you just want to toss it. You don't want to directly use, since it's impossible to get for one direction, right? Just place it perpendicular to the ground, and there's no chance that you are getting more than 1Gs, right? So there are some errors. So whenever it's larger than that number, let's directly just use 8192. So we're just trying to correct it directly using 1G instead of a larger number. All right. Same for the other direction. When it's smaller than that, then just use this one, the negative number as well. So what is this one? What is this one doing here? $57.296. What is that? So remember the A sign? Yeah, so you can convert the angle into radians. That's how you convert it. And I think I showed the calculation somewhere. You can find out why it's very straightforward to convert it into this number. And what about this one? The accelerometer raw data divided by 8192. What is that? So the acceleration data, because we are assuming that the angle here is tiny, okay? So you are measuring the acceleration in that direction, and the acceleration in this direction is 1g, okay? So A sine, for example, that's acceleration data. A sine, A acceleration data over 1g will be the angle here. You are thinking like, can I do A tangent? Sorry, double C. Can I do this as well? What's the difference? I mean, can I use this? I mean, do you understand the first one? Do you understand the first one before we move to the second? Do you understand the A sine? Because if we are assuming this is a 90-degree angle, I know it's not, but because the angle is super small, so we can assume this is 90 degree, right? So 1g XL data here. So 1g over, this is sine theta, right? Because this is theta. That's why A sine, oh, sorry. Right? Is that correct? Did you learn this A sine function somewhere else in physics? You did, right? But does this make sense? Okay. So are they different here? Can you use a tangent instead of a sine? Very similar because the angle is small. So a tangent and a sine. Because for a sine, you're assuming this is 90 degree. For a tangent, you're assuming this is 90 degree. Right? No difference because the angle is small. You're asking, like, you're wondering, what if the angle is huge? If you have a big angle, then they are not equal anymore because the a tangent, a sine has a more significant difference. Is that a valid question? No, because when the angle is too big, it's not adjustable. The car cannot make it back. It's just too big. It's going to tip over anyway. Okay, so whenever it's adjusting the position, trying to make it work, the angle must be small. Okay, so still adjustable. So a sine works. Okay, that's that part of the code. And now let's move forward. So got the gyroscope data. What is this number here? It's also given, right, by the configuration register. And here's the data fusion. You know, this has been very common if you look at the references and everywhere else, they are using this data fusion. It's a low pass filter. The reason it's a low pass filter is it's trying to filter out the big changes from the acceleration data. You know, you get two angle data, one from the gyroscope, one from the acceleration, all right? And then you do a data fusion, you combine them together by multiplying a very small number. You're taking a very small ratio from this angle data. But for the gyroscope data, you take a bigger weight from it, and you combine them together. I'm not saying we have to use it. I'm not saying like 0.0004 is the number we're going to use. I'm just trying to show you that this has been used for most of the references and it worked here. So that's why in one of the tasks, I want you guys to try, if we just use the acceleration data for the angle, can we still make it work? I don't know how much of the difference. Because the gyroscope data tested the angle change. So for example, it's changing the angle here, right? That's still the angle change. I mean, if you have a very small change over here, you are still getting a very small error, but it's not standing on the table anymore. It's already trying to tip over. But acceleration data is really comparing the this over 1G. I don't know how to visualize this difference, this change. I think the 0.0004 is also an empirical number being used. I recommend like we start from there and then try to adjust the number to see what's the difference, right? Why we have to, do we have to use this combination? Or if we just take more, give the gyroscope data a larger weight and this one less weight, will that work as well? Which I don't know. I mean, I just did this one and this works. You know what I mean? So the name of this variable, so that's the final angle data you are getting from the microcontroller. And that angle is still named as angle underscore gyro, but it's not the pure gyro data anymore. Because it's a combination of the gyro data and acceleration data at the same time. And then use that calculated angle minus 0 degree. So you are getting the difference, the error. How many degrees is it's leaving the 0 degree from the balanced state. Okay, so that's the error of the angle. So the error of the angle is already acquired, and we want to precise it in the PID controller. So the PID controller is going to give you an output from this error. Okay, so here's how you implement that PID controller. All right, is this part. So first, the integral. So it's just adding the past error. So the new error is being added to the past error. And you are thinking like, hey, if you are keep adding the errors, isn't it a positive control? Is you're just getting more errors? What's the trick here? When it overshoots, you're getting a negative error. So still adjusting your PID output to the step point. It's not, you are not having the errors in one direction all the time, right? Sometimes it's going to overshoot. So are getting a negative error. So it's going to bring it back. So all the P and I and Ds are trying to control it. When it's getting closer and closer to the set point, it's going to overshoot and then bring it back more efficiently. It's not like a linear adjustment, right? It's just directly adding. For example, if I only have the proportional controller, then what's going to happen? If it's only proportional. So here's the set point, right? I started from here. A P controller, okay? So you have a gain, right? So for example, I get an error here, as error 1, and the P controller has a coefficient to the error, which is like A times the error, okay? So I got a E1, so next time I'm gonna add, A doesn't have to be an integer, right? It can be a fractional number, okay? So I'm gonna add this, and then I'm getting here, it's getting closer, so I get another error. Okay, so I'm adding another one. Let's keep doing that. Ooh, it's already overshoot. Then what's gonna happen? I got a new error. Same state as this one. So what's next? What's this called? It's oscillating. Which is bad. Can never reach the set point. So proportional controller is bad. So sometimes you can use a proportional, the PI controller or PD controller, but never P. Okay, PID, sometimes works the best, but PIPD usually works as well. So we don't want to directly just do it linearly. Okay. So now let's come back here. So that's pre-processing of the I error of the I gain. So I gain was 0. So that's error. That's a angle difference. That's a degree in degrees, right? Since this was calculated by the two sensors, and that's I gain. We need a gain. Why do we need a gain? So look at the P controller first. You need a gain because you don't want to directly add that much, right? It's either this much of the error, right? So you need a coefficient. That's it. Just need a coefficient. It's called a gain, right? Gain of the error. So after you get the error, you need to multiply by something and use that multiplication in the system. So that's the I gain. You can adjust it. I mean, we don't have something really you can adjust. For example, what I'm thinking is for this project, probably it's better if we can visualize the change, the set point in real time. If I can directly design a GUI, which can show that set point and also the real data at the same time. So I can actually have design 3 knobs and which controls the PID gains. I can directly turn it while I'm looking at that curve. So I can visualize everything, but I don't have that GUI yet, if anyone want to do that in the future. I'm probably planning to see if we can implement that idea next summer. But I think that's a better way for you guys to really visualize the PID controller's performance, because right now the PI and D gains are really just the arbitrary numbers we created. It's difficult to get the real the optimized number for the controller. Okay, you have to manually change it. Like you manually change it, you reprogram it, and then look at the performance and change it again. So it's frustrating. So the I gain times the angle error, you are getting this one. This will be used because the calculation here is a little bit long, so I don't want to directly use this one in the calculation here, right? So that's the equation to find out the overall PID output. You know what I mean? The PID output is just directly the errors processed by the PID, the 3 controllers, and you get these output and add them together. It's very simple if you look at here. Right, so this is how I calculate it. So the set point, subtract the output right at that point, and then you got an error. So error is being processed. This is a function of the time. It's the ET. And ET is being processed by this as the P gain. KP is the P gain. Ki is the I gain, Kd is the D gain, differential gain. So delta T is exactly 4 milliseconds, right? That's what we define for the controller. And you add them together as a sigma here. So you add all these output together to get the PID output. See here. You add the output of the P and I and D controller together to find out the PID output. Okay, that's how that works. So we started with a component of the I controller, and now let's see, where is that in here? It's here. So why do I name it as MEM? It's like memory. Okay, just memorize the operation at the very beginning. So you put it here as an I component for the PID controller. And what about the second line? If this is larger than 400, then give it 400. So to control it, so it's not overshooting. Where the 400 comes? It's also not calculated. It's looking at, so at the very beginning, you set up all the gains at some point, and then you can find out the PID output. If it's too much, then you don't want to just directly let it go to the very large numbers, because it's going to overshoot the over the set point. It's the same for the negative values. So we just control that the adjustment within a range is plus minus 400 instead of going too high or too low. And this is actually critical. If you do not set a range, then it's going to over adjust the angles of the car. So do we have the proportional component of the PID controller yet? It's very simple, right? Remember, the proportional component of the PID controller is only Kp times the error. Where's Kp? That's a constant, which is defined at the very beginning of the code. And times this one, it's also still the error here, angle error here. So that's a P component. That's the I component. That's a D component. It's a differential error times the D gain. Where the D gain came from? It's just an empirical number. So you set up, you just throw some gains over there, like 10, 20, 30, things like that. And then you can find out the PID output. And that PID output will be in a range. And so that's why you get the 400, negative 400 like that. Okay. The current error minus the last error, that's the difference between the two states. So the overall calculation here is going to get you the PID output. And still the same, you want to control the overall output within the 400 range. All right. And eventually the PID error is assigned to the last error, because it's going to be used for the next cycle calculation for the D component of the PID controller. See here, it's going to update the last D error. Okay. So what was this part? That's the last part you need to pay attention. No, the second last. So whenever the angle difference is within 5 it's not degrees. It's already processed by the PID controller. So the PID output is within 5 and -5. It's not 5 degrees and -5 degrees. You know what I mean? Because the PID out here is already calculated by the PID controller's process. It's not a degree anymore. It's a number right now. Doesn't have any unit. So if that one is within 5 and -5, which means it's not falling forward or backward with a large angle, we can consider that the car is balanced. So we don't want to adjust the movement of the wheels anymore. You know, it just consider it's balanced. Then give the PID output 0. So whenever you have a PID output to be 0, you are not trying to move any of the stepper motors. So here's the main technique being used over here, okay? Delay to be added, delay to be added. Let's just remember this code right now, but I'm gonna explain that over here. So when the PID output is 0, I'm not adding any delays. To where? To the interrupt later. I'm gonna explain that pretty soon. Because that's the most important part. That's how you can understand this code, all right? Otherwise, you have to convert the PID output into a number that can give you a linear output to the stepper motor. And this is another part. It's difficult to understand, but I'm going to write it on the paper pretty soon to show you that. Any questions by far? So you're asking, like, do we have to use 400? No. 420, -400, fine. It's all the numbers defines the behavior of the car, how much it's adjusting itself, and how much you want to stop adjusting that. Is there an alternative way to achieve the same goal? Yes. Okay, if you can find out, which is great. So if you do not set up the range for 400, -400, what the car is going to do? All right. I think I tried it last year. I forgot, you know, what was the result. But if you want to try it, definitely do it. You know, it's just trying to, because whenever the car is moving really fast, there might be some random PID output can be very, very large or very small, like very negative, then which is going to directly being fed into the movement of the stepper motor, and it's going to be out of balance. So that's why it's trying to maintain the PID output within a safe range. So it's not moving too much. All right. Okay. So at the very bottom, so these two lines, I have explained that for multiple times. It's just trying to keep the loop function, the time for the loop function to be 4 milliseconds, and that's it. Remember, if you cannot remember like what this one does, go back to you can revisit the first video we had for the balancing robot. All right, now the most important part, the interrupt routine. ISR, interrupt service routine, okay? So how long this is being triggered every time? That's the most important part. If you cannot understand this part, you cannot understand anything about the car. Okay? So this is the most important. Second important part is the PID controller's calculation. And here's the most important part. How that works. Everything in the loop function didn't do anything except for setting the time to be 4 milliseconds first. Second, get a PID output from the angle. That's it for the loop function. Now here, the interrupt service routine, what this one does. So at the very beginning, it counts for how many times it's been getting into this interrupt service routine. So we got a counter here, and look at the bottom. Only when the counter is 1, So we are going to look at the details of this first. But now I want to let you know, these two lines is just to giving a step to the motor. It's giving a step to the motor. Why? We'll come back later. Not right now. It's too much information. Okay, just remember these two lines is going to give a step. How many angles per step? 1.8 degrees. Okay. So these two lines is giving a pulse to the stepper motor. All right. So the first time it enters the interrupt service routine, the counter becomes 1, and it's going to give a step to it. So the second time it enters the interrupt service routine, it doesn't meet this requirement anymore. So it won't move the stepper motor. So what does that mean? So keep in mind, just think about that one first, okay? Now move to the next line. If the counter's value is larger than the delay to be added. So what's that variable? Delay to be added. What is that? See here, that's how we calculate it. So the delay to be added is a number calculated by the PID output. So let's don't, get into the details of this calculation yet. But it's a PID output will be converted into delay to be added. So what's happening over here is, that's 20 microseconds. And how many 20 microseconds you want to add to there? So that's delay to be added. Sorry, not there. That's delay to be added. So what's being done over here is, if the angle, the degree difference, or the angle, the current angle compared to the original angle, if this one is bigger, then what's going to happen? The PID output will be bigger, and the time to be delayed, the delay to be added to here. So because one pulse is going to trigger one step. When the angle is bigger, you want to wait for a lot of time to trigger the step, or you want to just directly, trigger the step immediately. Trigger more steps immediately when the PID output is bigger. Trigger faster. You want to add more delays to it, right? So here's a question: how do we calculate it? So when the PID output, so let's just, I'm going to show you how to get this function later, but now it's in a denominator. So when the PID output is bigger, it's adding less delays. Does that make sense? You don't want as much delay over here. So you have options. So I'm thinking if you show this, if you make a connection, your probe, that pulse, that step being sent to the stepper motor, to the oscilloscope, you are going to see this with the different duty cycles, right? So the duty cycle here will be changed in real time, depends on the angle. So whenever the car is balanced, you are looking at the oscilloscope, what's going to happen? You are going to have a pretty evenly distributed pulses with this 20 microseconds pulses, because it's not perfect, it cannot be perfectly balanced, right? There will be some small degree changes. But the thing is, it's very stable, so that's why this is evenly distributed. But however, whenever you push it, right, it's gonna swing back and forth. Then what's gonna happen? If you look at the oscilloscope, you are going to see a lot of pulses. All right, so that's how you do the PID controller. So whenever the degree is larger, you just add more pulses or less delays. How the delay is added? Let's look at the code. So large PID, large angle, less delay. How that is implemented? When the delay is less, which means this counter can reach this number quicker. Okay? Then it's going to come back and reset the counter quicker. So the counter can come back to 0 quicker. So it is able to count to 1 quicker because it only triggers that movement when counter is 1. So don't look at the code. Let's just directly describe it. All right. First, remember, it only triggers one step when counter value is 1. Okay, remember that. Forget about everything. So only boom, do this when counter is 1. But the thing is, it has a counter have an if statement over here. It's gonna, after it enters that interrupt service routine for every 20 microseconds, right? It's gonna start counting from 0 to 1, 2, 3, 4 until a number. Until it reaches a specific number, then it's gonna clear itself, which is this line does, and then you get a chance to get counter equals to 1 again. So if that number is large, it takes longer time to come back to clear itself, so you get another chance to count to 1. If the number is small, if the goal here is small, then do you have more pulses or less pulses in a certain period of time to trigger steps? Okay, see here, look at my hands, okay? Yeah, so look at my hands. So that's the overall number over here, right? I have a counter, it's counting from here to here. I can only trigger a step when the counter moves to 1, okay? And then I'm gonna clear myself. Then it's gonna start counting to here, and then come back to clear itself, equals to 0, right? So that's how you clear itself. And then you get another chance to count to 1, then you can trigger another step. So you have a longer time here, then it takes a lot of time until it comes back to 0 again. If you have a smaller time period, then it's from 0 to 1, done, come back to 0, 1, done. So whenever it comes to 1, it triggers a step. Okay? So that number is a variable here, the delay to be added. How do you calculate that number? How do you calculate that range? Like when you want the counter count to? From the PID output, right? Because the PID output should determine how long I should have over here. But now here's the question. If the PID is bigger, then that means the angle is bigger or smaller, the PID output. Bigger, so you got a bigger angle difference, you got a bigger PID output. So the bigger PID output you have to convert it, use the transfer function to convert the PID output into this time delay to be added here. So a larger PID output, a smaller period or larger period, or a smaller delay or larger delay. Smaller delay. It's going to trigger that step more frequently, right? So how do we calculate it? Here's the transfer function. How do we calculate it? Okay. So you want to convert. You want to convert the PID output to what? So what is actually moving the car? Speed, velocity. Is that correct? So the PID is bigger, a larger angle. I need the car to move at a larger velocity, which is meters per second. Okay? Let's see the numbers. So the frequency equals to 1 over t plus x. So for example, here is 20 microseconds. So this determines the frequency of the pulses. How many steps I want to add to here? How many delays? So they are not giving pulses, but it's adding delays. And they are all 20 microseconds delays. Because the ISR is being triggered every 20 microseconds. Okay, so the overall period over here will be 20 microseconds plus all these time delays. This is x. This is how many? These are x. All right, so that's the frequency of it, because 1 over the time will be the frequency. What's the unit of this? Does that make sense? So this will give you how many steps per second, and we want to convert everything to meters per second, and how? So steps per second, and so what's the perimeter of the wheel? For example, this is R. Okay, so P equals 2, so the perimeter equals to 2 pi R. Is that correct? And then P over 200 is what? So this is meters per step. So P 200 times F prime, which is giving you this times this. No, so I think this is wrong. This should be, because all these are delays and there's only one step. So this is actually step per second, right? That's just one step, how long it takes, right? That's a one step per second. So you can cancel these two, and this is giving you meters per second. That's the velocity. So this is P over 200 times 1 over T plus X. So X is how many? 20 microseconds. T is 20 microseconds. And this can be very similar to, this is way larger than 1. So you can directly just use So this is not giving you an accurate transfer function. You still need a coefficient, whatever, into like a gain, a coefficient to adjust the performance of the controller. But anyway, so this will be the final transfer function. So the x, which is the delay to be added over there, is at the denominator of the function. So this is how you can get this. I mean, you're asking like, why is 5,500? Why is plus 9? It doesn't have to be that. It just have to be what? If you're looking at this function. So all these are constant, are they? It's a constant. And I just have to add another coefficient, which is like, depends on your testing. You find out like, I need to add another coefficient here. So overall, you just need a something times 1 over x. Okay, and what is that saying? You have to test it. I don't know. Keep adjusting it. That's how you can adjust the controller, make it until it's perfect, based on your visualization. I don't know. It cannot be perfect on the theory. So this is a overall function here, and this is how you make it work here. You know, it doesn't have to be this. It just have to be, so the PID output just has to be at the denominator. That's it. And just times the, you don't even have to plus the number here. So another question, why it has to be this for the delay to be added? Why is that? It's trying to make things linear, trying to add. So whenever you have a PID error, it's trying to add a time delay here, because right now we are adding all these 20 microseconds time delays. And how can we make it linear? Like I have a PID controller value here, P already. And how do I know like how many I want to add to here? If it's not linear, then whenever, so for example, when the angle changes at a different location, it's not going to adjust the angle with the speed of the wheel at the same rate. You know what I mean? It's not linear, because whenever the angle, like for example, it changes here, changes a little bit, right? It's gonna, whenever angle changes by 1 degree, it changes the speed by 1 meters per second, right? And when the angle changes like 2 degrees, I'm changing the speed like to 10 meters per second, which is bad. So it's not, it's gonna oscillating, and it's gonna tip over instead of linearly adjusting the output. And the way you can make it linear is this. Why? This is not linear, right? So 1 over x is not linear. What 1 over x looks like? This. How can I make it linear? That's 1 over x. How can we make this linear? How can we convert it into a linear equation? We force x to be 1 over x. Then what you're getting is this. All right? So the way to make it linear is to change x to y and add a coefficient to it. So the coefficient only changes the slope, but it's still linear. Be this, or this, right? Depends on the performance of the PID controller. All right? Have to think about it. It's definitely not the only solution to it, but I think this is a really interesting algorithm to solve this real-world problem. And I'm still exploring it, see how we can really visualize the performance when I modify the PI and D gains. But I haven't found a way to do that. It's either going to be a GUI or have to look at it from the oscilloscope. But I think you guys have enough information to process in order to get the car work. So I'll be around to help you guys, and I'll give you access to 670 as well. Have enough space to work on this project. All right, we'll see you on Wednesday.